Hello everyone, and welcome to this video, Kerr geodesics number 21, the second video in this current pair that looks at the finding equations of motion for a particle in the four-dimensional space-time, the Kerr geometry. So this video I'll look at how to derive expressions for two of the components of the fall velocity of both massive and massless particles, that's the r dot and theta dot components, using three known constants of the motion: the energy of the particle, its angular momentum about its axis of rotation, that's the phi component, not the theta component, and the Carter constant. And there's one other I should mention too, and that's the Hamiltonian. We should use the constant that comes from the magnitude squared of the form momentum. Okay, or is related to it. So this follows up from the Kerr geodesics number 20 video. The two go together. So let's have a look. All right, so what we're trying to do is, will that fit in there? Yes, that'll fit in there. Remember, we've got some particle with mass, or it could be massless. Let's talk about the mass case first. With mass, and it's freely falling in the Kerr geometry here. Now, here's its world line, some path it's followed. This is not just motion restricted to the equatorial plane. This is now just motion in general in the r, theta, phi, and t directions. So the world line of a particle, the geodesic it follows, has a tangent vector at each and every point. The components of that tangent vector are ct dot, r dot, theta dot, phi dot. In the last video, number 20 in this series, we found ct dot and phi dot, which was we actually found right back at the beginning in the first two videos in this series, but I just gave a different take on it in the last video. We parameterized the path x of mu in terms of parameter lambda. For a particle with mass, lambda would be the proper time tau of the particle. That's the time it measures if it had its own little wristwatch and carried it with it, or carries its own clock with it and could measure its own proper time. For massless particles, we have to use parameter lambda. We can't use proper time. The derivative with respect to lambda of the coordinates is x dot of mu, and they give us the components of the fall velocity of the particle. Now, the whole point of this video, number 21, is to find r dot and theta dot. In the last video, immediately preceding this, we found ct dot and phi dot. Okay, let's remind ourselves of motion. So the fall velocity is tangent to the world line of the particle, tangent to the geodesic, and that fall velocity of a freely falling particle is parallel transported along the geodesic. So its magnitude and direction are held constant as it's moved in infinitesimally small steps. This tangent vector is held parallel to itself. It keeps the magnitude and direction constant. So the magnitude squared is minus c squared for the particular metric signature I use on this channel, which is -1 plus 1 plus 1 plus 1. That's the only metric signature I use. Just be aware in other textbooks, other sources, the opposite signature can apply. So you have to be careful in interpreting material in relativity where different signatures are used for the metric. Magnitude squared of the fall momentum, minus m squared c squared. All right. Now, in the case of the components of the fall momentum of massless particles, what we can do is rescale these coordinates to give us the value of the form of each component of the fall momentum of a particle. So a bit of photon, something might use wavelength or something like that. And so we rescale the coordinates. So the fall momentum for a massless particle, photon, graviton, maybe some neutrinos, would be x dot mu, e mu, basis vectors e mu. So, and all that is just the components are given in terms of the derivative of the rescaled coordinates x dot mu. Okay, so the point of this video is to find r dot theta dot. All right, let's move on. All right, now, let me stick that there. Or just for the moment, hide it. Okay, so the Hamiltonian is given by, it's a function of the coordinates x mu, the derivative of the coordinates, and the parameter lambda. And it's given by p, the covariant components of the fall momentum, and the derivative of the coordinates, the contravariant components, minus the Lagrangian, okay, and that can be written out. P mu can be written as m g mu x mu dot mu minus the Lagrangian, and as we found in the previous video, the Lagrangian for a free particle is just this, and then the Hamiltonian gives us this object minus that, and which is just equal to the Lagrangian. So the Hamiltonian of a free particle of this Kerr geometry is just the Lagrangian. The Hamiltonian can also be written in terms of the magnitudes, in terms of the momentum, for momentum as m squared g mu. This here over 2m. Each of these p's has a mass m for a particle with mass. Massless particles, we're just going to drop, and we just use rescaled coordinates x dot mu. Okay, but for a particle with mass, we would have this. And I will work in terms of, though we have a particle of mass, but you just drop the m's and think in terms of rescaled coordinates for massless particles like photons, gravitons, and so on. Okay, like this. So working with this gives us 1 on 2m g mu nu, each of the components of the form momentum, the contravariant components, and that's equal to L. And we can write that as this, which, contracting with the metric, using the metric to contract these two components here, u mu lower, gives a half mc squared delta, where delta is -1 for time-like geodesics, followed by particles with mass, and delta is 0 for null geodesics, that's particles, geodesics followed by massless particles. So for massless particles, null paths are followed, delta is 0. For massive particles, that's particles with mass, then we have time-like geodesics, so -1 for delta. All right. Next slide. Okay, so the Hamilton-Jacobi equation is this, plus ds d lambda, and we'll get at what S is. But when we solve for S, this equation here is equal to 0, and this will help us find expressions for r dot and theta dot. So ds d lambda, well, with the chain rule, ds dx mu d lambda. So dx mu d lambda is just x dot mu, okay, the derivative of the coordinates. And we can write that as 1 on m g mu nu p subscript mu, okay, from previous slide. Putting this in here, h plus this object is h plus that, h plus this here, 0. So, and remember, h had this value from the previous slide, minus a half mc squared delta. Then we have 1 on m g mu nu ds dx mu, p nu is 0, and we that then suggests to us that ds dx mu is a half p mu, which is a half p mu, or p, the covariant component of p is p subscript mu equals 2 times ds dx mu. All right, so we have this object here, and that's equal to 0. So we want to find an expression for this S in here, okay, that will help us solve this equation, the Hamilton-Jacobi equation. Now, writing out these components here, we get this expression here. So we get minus a half mc squared delta here, plus 1 on 2m, and then writing out each of these components, gtt, this, gt phi. Remember, there's two of these because you have t phi and phi t, and they're both the same, identical, these metric components, p phi and so on, and then g phi phi, grr, g theta theta, and all of that is 0. All right. So what does that tell us? Well, let's look at the next slide. So the constants of motion we have so far, that's from videos 1 and 2 in the at the beginning of this series, and then we're just in the previous video, number 20, just reminding ourselves that h, we found cpt is minus e, or pt is minus e over c, and the phi component momentum is the constant h. So these are conserved quantities, these two, as is this. All right, it'd be handy now because we know we have 4 of these derivative components, ct dot, r dot, theta dot, phi dot. There's 4 of them. Now, we could find ct dot and phi dot because we had these constants, these first integrals, which of Lagrangian, of the Euler-Lagrange equations, which gave us these. Could we do the same for r and theta dot? Well, we have a third constant, the Hamiltonian here, and there is going to be a fourth constant, it's the Carter constant, and this is what we're going to try and find. So let's suggest a solution of the equation from the previous slide. It has the form S is this, and some r theta term here. And what we're going to suggest is we're going to posit even further, like an ansatz, or we're going to conjecture that the final form of the solution will be S is minus a half mc squared delta lambda minus et plus phi times h, okay? And then a function of r, and then a separate function of theta. Okay, and just to remind ourselves on the previous slide, we had this object here equal to 0. So let's see what we can do with that. Okay, now put that one back. Okay, so here we go. Substituting into that previous expression with the components of the form momentum. Remember, P subscript T was minus E on C, PT here. P phi is the H, P phi is the H there, and PT is minus E on C. Then we have G phi phi HH. Now we have GRR 2 DSDR times 2 DSDR and DSD theta twice. Okay, it's these with DSD thetas and DSDRs we'd like to find. So let's keep going. We've substituted this in. That's our next line. Okay, because remember we could combine we'll also be able to combine these. Remember, got to go careful with the minus signs here because you have two negatives here with cancel out. Don't forget, ultimate GTT is negative itself, and GT phi will be negative. So just got to be careful because if you're going to have problems with this, as I discovered, it will occur in the algebra here with the signs. And you get them wrong earlier on. Later on, it'll carry on and there'll just be errors and it'll be frustrating. When you go back, you actually find if you're not careful with the negative signs here, you'll get yourself into a bit of trouble with the algebra. And that's all it is. It's as simple as that. Okay, let's remind ourselves here, these inverse metric terms. Now, if we go back to video 12 in the Kerr metric series, not the geodesic series, but the metric series, we found these. We know an expression for that. GT phi, G phi t is this. GRR was delta on rho squared, G theta was 1 on rho squared, and G phi phi was this object here. And we know an expression for that last bit in the parentheses there. All right, what we're going to do is use these to substitute into here as our next step. All right, so the last metric term can be rearranged to give G phi phi is this. Okay. Now we found this part here in the previous video to this, the one immediately prior to this video. So I put that in there. When we do that, we come down to this object here. So that'll be handy. Now, just put this equation down here to remind us what we're trying to find, because we've got to substitute in GTT. Each of these inverse metric terms, components we have to put in. That'll be next. Okay, so we get minus a half mc squared delta minus all this. Okay, make this substitution we found from the previous video. Put that in there. Then what we're going to do is multiply through by rho squared. No, it says rho squared there, 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 and there. So simplify the expression by just simply factoring it out because it's all equal to 0. When we do that, we get this object here. I hope my picture's not in the way there. So we get this object here. All right, like that. Then next step, let's keep going. All right, now we've got this object here. Okay, notice I've substituted this in, and ultimately we'll replace this one a little bit later on. So tidy up some terms here, get them all together. All right, tidying it up again. We have all this. Next thing we'll do is all this is equal to 0. So we're going to separate the r and theta terms. So we'll get all the r terms on one side and the theta terms on the other. And when we do that, if you notice here, so this dsd theta will go over to the right and become negative here. This one on sine squared term will go over to the right. That'll become negative. This bit here with a squared cos squared theta will go over to the right. It'll become positive. And these in terms of the r's, remember delta only has r's and a's in it. and that'll go over to the left here. So we've got all the r terms on the left, and all terms involving r, that is, and all terms involving theta on the right. Okay, remember they were equal. The whole thing was equal to 0, and we just took all the theta terms over to the right. Next step. Now, maybe I'll hide that for a bit. We're going to add this constant term to both sides. All right, when we do that, we get this bit here, and on the theta side, we'll get this bit here. Then we're going to start collecting terms, putting things together. So we'll have this here. We've got all this. I've got delta. Yep, here we go, like this. We're going to start looking for things that we can combine. We'll be doing something shortly with this term here, 2gmra on c squared delta. That one there, very important when you're doing this. I referred earlier, if you didn't get the signs right, you'll have all sorts of problems. And the first time I did this, when I didn't get the signs right, I had a 4 here, and it just wasn't working out. And it was just a simple matter of going back to those steps a couple of slides ago, making sure the signs were correct. Where there's a negative sign, make sure you follow it through. If there's 2 negative signs, multiply together, all the rest of it. You just need to watch your algebra there with the signs, otherwise it'll give you endless trouble with the algebra. Okay, so we're starting to collect some terms here, put them together. Okay, I believe down here we've got cos squared here, and we've got common denominator sine squared, and then here 1 minus sine squared became cos squared. Okay, keep going. Now we're going to make this substitution, and I mentioned this substitution earlier, I think, in this video. It might have been in the previous video, but anyway, here's the substitution we're going to make, and that will go in where I had that business I was pointing out to you on the last slide about the minus signs. Be careful. So let's substitute that in. So we get this object here, goes in here, here it is, minus AEH on MC, there, and that bit there. Okay, this bit here. And then we're going to start tidying a few things up, because the next thing will be that take out a factor 1 on 2m, 1 on 2m delta actually, so 1 on 2m delta, and then we're going to have an e squared on c squared times all that squared. And so what we're going to do is just have e on c times that all squared minus the AH. When you expand that out, you'll have this bit all squared, which gives you this bit here, 1 on 2m delta, 1 on 2m delta, all squared, and you'll have this term will come out here, because 2 times all of that will give you minus 2AH times all that. Minus in front will give you the plus. And the 2 here will cancel with this 2 down here, so we get A times EH on MC. Okay. And this area here is where I had all the trouble with the minus sign earlier, so be careful when you're substituting. And then over here, minus AH all squared is plus, will give you here A squared, H squared on delta 2m. And don't forget you have the negative sign out front, so that makes it all minus A squared, H squared on delta 2m. Then you have the constant term that we added earlier equals all this. Okay, then next line down. So we have that plus that. And what we're going to do over on the next slide, we'll start tidying this up as well, finding a shorter expression for that. Okay, so we get all of this here, and factorising that last bit I was just telling you about a moment ago, we get 1 on 2m E A on C minus H all squared, and then this theta part was still not touched. Okay, but we'll start to work on that now. So we've got this top line, all the R's there, equal to now all the theta terms here. And we've just tidied this up a bit. So we've got a factor here. We've taken out cos squared theta from here, here, and here, sitting out there, and then we're left with a half mc squared delta plus 1 on 2m e squared on c squared times a squared, that bit in there, minus h squared on 2m sine squared theta. Now, left-hand side, r's only, right-hand side, theta's only. All right, so the left-hand side does not depend upon theta, it's r only, and the right-hand side does not depend on r, so it's depends only on theta. For that to be true, all along the geodesic followed by the particle, both sides must be equal to some constant. Okay, that constant turns out to be called the Carter constant. It's not, it's a constant that is of a mathematical nature. It's not a physical constant like E and H that we found at the beginning of this series. It's just a mathematical constant. Whether it has any physical significance or not is not sure. So here we go. We have the R's here. That's equal to minus C, and then we have the okay, that's equal to minus C, and then what we're going to do is bring that minus C over. So we have 2 delta on M ds dr all squared is equal to minus C, the Carter constant, plus all of that. And then multiply through by M on 2, give us all this. So we have delta times that. Okay, and then what we can do is we'll group these terms together and this one over here, and we'll multiply by another factor of delta. So we had delta times all this. Down here we'll have delta squared times all that. So we'll have a factor of delta here times all that, and this multiply again by delta will cancel this one out. So 1 on 4, all of this. And what we do is we call that whole bit on the right there, we're going to call that capital R. Okay, just give that a name. We'll call it capital R. And so delta squared ds dr all squared is R. So that implies that ds dr squared is R on delta squared, and ds dr is plus or minus square root R on delta. The plus or minus comes in concerning direction, ingoing or outgoing. There's 2 directions there. That's the R part. Let's have a look at the theta part. Similar thing with the theta part. That's equal to the Carter constant here, and what we're going to do is multiply through by minus 1, get that, then bring C over here. Actually what we're going to do is take this cos squared term and factor here over to the right, so we'll have plus C plus all of that, then multiply through by M on 2, and then we're going to call this capital theta. So we'll give it a new name. All of this is capital theta. Give it a new name. And so ds d theta squared is capital theta. And so ds d theta is plus or minus the square root of theta. Again, direction. Theta going down in the conventional polar sense, plus, and theta up in the conventional sense is minus. All right. So direction, and so you've got 2 directions, up and down, if you know what I mean. Now, the solution to the Hamilton-Jacobi equation S has this form here, and from an earlier slide, ds dx mu is a half p mu, or implies that p mu is 2 times ds dx mu, and x dot mu is 1 on m g mu nu, the inverse metric term p nu. All right, so for massless particles, we would use I should have removed the M from there. Just use rescaled x dot is this. My apologies, the M should be gone from there. I meant here for massive particles use this. And then for massless particles, just use that. My fault there, that M should not be there for massless particles. All right, so what do we have so far? What have we found? Whether they're particles with mass or without mass. So we've got R dot is 1 on M GRR PR. So 1 on M GRR is delta on rho squared times 2 dr ds. Remember, PR comes from this thing here. PR is 2 ds dr. And then we have plus or minus 1 on M delta rho squared 2 square root R on delta. Remember, ds dr was square root R on delta, plus or minus. So we have this. All right. And what we're going to do now, our very next step then is to rewrite that as rho squared R dot is plus or minus 2 on M square root R. Theta dot, same thing, exact same process, just follow that through. And if we multiply both sides by rho squared, we get rho squared theta dot is plus or minus 2 on M square root theta. And so the point of all that is if the components of the tangent vector to the world line of a particle are then rho squared ct dot is all of this. I mean, if you just want ct dot, just divide both sides by rho squared, of course. But it's convenient to express them in this form. Rho squared R dot is this. Rho squared theta dot is this. rho squared phi dot is this. Now these are the components of the the tangent 4 vector, or the 4 velocity of the free particle. Okay, and if we wanted to plot that, we could plot the tangent vectors, or we could numerically solve it. We'd have to numerically solve it to plot the spatial part of the motion of this particle. We'd have to numerically solve it, numerically integrate, and then numerically plot. So R is this object here. Capital theta again is this object here. And there are our 4 objects. So we could plot motion in 3D, the spatial part anyway, using ct dot r dot theta dot and phi, r dot theta dot phi dot. Okay, we could plot that, but we'd have to numerically plot it. So it's numerically integrate, because remember R, capital theta, and all this over here are functions of R and theta. And to anti-differentiate this, in here you've got R and theta already. So it has to be done numerically. It can't be done, but we do have explicit components for theta, phi dot, R dot, and ct dot. So that's good. All right. And then numerically solving and plotting will give us the path of the particle. And the Carter constant C, as you saw earlier, how that works. And I think that's it. I think that was the last slide. So these results can be used to numerically plot the motion of a particle, because we have these components here. And so we could plot this geodesic, or the spatial part anyway. And I think that's what I have. So thank you very much for watching. A little bit longer this video, and I'll see you in the next video, in which I will look at a paper published by some researchers that have developed a mathematical tool for plotting these geodesics. All right, thank you everyone, and bye.